Hello everyone, in this video I would like to talk about the techniques used in the commercial code STAR-CCM Plus to model mesh motion. Generally, motion refers to the alteration of an object's position relative to a designated reference frame. In the field of fluid mechanics, a segment or a portion of the fluid region signifies a part of space that is traversed by material flow. In this scenario, the fluid computational domain is adjusted to reflect alterations in the shape and location of the boundaries which may occur due to the movement of neighboring bodies. Some instances of flows induced by motion include turbomachinery, ship and propeller motion. Here we address the mesh motion in transient and steady state simulations. Mesh motion in transient simulations. In applications of fluid mechanics, the mesh can be moved rigidly according to specified translations and rotations, as shown here in this figure, or by employing the morphing technique, which accommodates for non-rigid deformations. Fluid regions can also be integrated with 6 DOF, degree of freedom, rigid bodies during dynamic fluid body interaction, DFBI analysis. In this scenario, CFD computes the movement of the 6 DOF rigid body as a reaction to the forces applied. The fluid mesh is then either moved rigidly, DFBI rotation and translation, or adjusted through morphing, DFBI morphing motion based on the determined motion of the rigid body. Another method to manage mesh movements is by utilizing overset meshes. Adaptive mesh refinement can also be implemented for this purpose. Dynamic fluid body interaction. Dynamic fluid body interaction, also refers to as DFBI, enables the simulation of the movement of a 6 DOF body, incorporating the displacements and rotations derived from specified mechanical and multiphysics interactions. At each time interval, CFD applies the resultant force and moment to the rigid body and resolves the governing equations of motion to determine the new position and orientation of the rigid body. 6 DOF body, rigid body. A 6 DOF body represents a rigid body whose motion is determined dynamically by the different forces and moments applied to it. Note that, as shown here, the movement of a three-dimensional rigid object that can move and rotate freely in any direction possesses 6 degrees of freedom. Based on this figure, Tx, Ty, and Tz represents the shifts or displacements along the x, y, and z axis accordingly. Rx, Ry, and Rz denote the rotations around the x, y, and z axis respectively. Unconstrained 3D rigid bodies are commonly known as 6 DOF, which have 6 degrees of freedom. For unconstrained 2D rigid bodies, the degrees of freedom decrease to 3, allowing them to translate along the two axes of the 2D plane and rotate around the axis that is perpendicular to the plane. Additionally, the movement of a rigid body can be restricted by limiting its translation or rotation in specific directions. Such constraints diminish the overall number of degrees of freedom. Two categories of 6 DOF bodies exist. One, a continuum body is utilized in scenarios where the 6 DOF body needs to engage with the flow and other physical factors to determine the forces and moments acting upon it. At least one continuum body must be defined for a DFBI simulation. An example of a continuum body is CFD simulation in seaways. Two, a mechanical body is a solid structure that does not engage with the flow or other physical phenomena except for the influence of gravity. It is applicable in situations where the effects of flow interaction can be disregarded. Nevertheless, a mechanical body remains affected by external forces and moments. For a 6DOF object, it is adequate to represent the motion of a specific point within the object along with its rotation around that point. This specific point is frequently the center of mass of the object. The relative movement of any other part of the object can be inferred from this point. Prior to calculating the rotational motion, it is essential to know the object's mass moments of inertia with respect to a designated reference point, which is again the center of mass. The mass moment of inertia of a solid object determines the amount of torque required to achieve a specific angular acceleration around a rotational axis. It is influenced by the object's mass distribution and the selected axis. To simulate DFBI motion in STAR-CCM+, one needs to estimate the body's moment of inertia and its center of mass. Depending on the available degrees of freedom, you can input the necessary component values while disregarding the others, as they don't contribute to the calculations. For instance, if the body is allowed to rotate around the y-axis, as shown here, only the component Iyy is needed. For objects restricted to rotation within a plane, it is sufficient to account for the moment of inertia around an axis that is perpendicular to that plane. In the case of bodies that can rotate freely in 3 dimensions, their moment of inertia are represented by a symmetric matrix, as we can see here in these equations. If the CAT definition of the object is available, the moment of inertia and center of mass can be calculated in 3D CAT inside STAR-CCM+. To determine the moment of inertia and center of mass, right-click on the object in 3D CAT and select Properties, as shown here in this figure. A mechanical body is not linked to a volume mesh. As a result, you should choose geometry components rather than selecting region boundaries to depict the mechanical body in visualization scenes. The mechanical body is constructed to exert force and momentum to change the behavior of other bodies, but it does not engage with the fluid. One notable benefit of the mechanical body is that it does not need a volume mesh. It only requires properties such as moment of inertia and mass and connections. From this point, forces can be applied, and through connections, these forces will result in motion and exert force on the fluid by linking to a continuum body, as we can see here in this figure. DFBI motion. The DFBI motion is selected to appropriately adjust the mesh vertices around a moving 6DOF body. Various DFBI motions utilize distinct approaches to modify the mesh in relation to the body's movement. STAR-CCM Plus offers 3 types of DFBI motions. DFBI rotation and translation. This motion transmits both rotational and translational movements from the 6DOF body. The computational domain, in this case, moves rigidly along with the 6DOF body by applying this motion to a region. DFBI morphing, this motion also conveys rotational and translational displacements from the 6DOF body. When this motion is assigned to a computational domain, that domain does not move in a rigid manner with the 6DOF body. Rather, the mesh lines between the 6DOF body and the outer domain boundaries are deformed to reflect the displacements of the 6DOF body. DFBI embedded rotation. This motion requires both an inner and an outer computational domain. The inner domain, which encompasses the 60UF body, receives both the rotational and translational displacements of the 60UF body. The outer domain, separated from the inner one by an overset or sliding interface, only obtains the translational displacement of the 60UF body. Thus, there exist relative rotations between these two domains. Conservation equations with mesh motion. Mesh motion has various interpretations in solid mechanics and fluid mechanics. In fluid mechanics, an Eulerian approach is utilized where a specific area of the computational domain represents space through which fluid flows. In this scenario, the fluid mesh is adjusted to reflect changes in the shape and location of the boundaries, for instance, due to the movement of nearby bodies. Modifications to the mesh motion affect the conservation equations by adding an extra flux to the convective terms. If the motion is described relative to a moving reference frame, the momentum equation incorporates fictitious forces resulting from the non-inertial reference frame. The most comprehensive situation is when mesh motion is defined concerning a moving reference frame compared to the laboratory reference frame. The conservation equations in the case of a stationary mesh are presented here: mass conservation and momentum conservations. Here, the bar sign refers to the mean variable, and omega is an arbitrary control volume which is bounded by the control surface S. V here is the mean velocity vector. The first term on the left hand side of the momentum equation shows the rate of variation of the momentum within the volume omega. This term here is the convection per unit volume through the control surface S. This term here represents the mean isotropic pressure component. Tau V here is the tensor of mean viscous shear stress, and tau R is the tensor of mean Reynolds stress. And finally, this term here indicates the body force. The conservation equations can be written in terms of the fluid velocity in the laboratory frame, also called absolute velocity, as we can see here, mass conservation and momentum conservation. Here, Vg is in fact the grid velocity in the laboratory reference frame, and Vr is the relative velocity defined as follows. Mesh motion is described in relation to a reference frame, which may either be stationary, the laboratory reference frame, or may undergo rotation and translation relative to that frame, as shown here in this figure. In simulations that are steady or transient simulations where time accuracy isn't essential, using moving reference frames allows the modeling of rotations and translations as a steady state problem while keeping the mesh fixed. Imagine a moving reference frame, MRF, that is both rotating and translating at a constant velocity, as we can see here in this figure. The speed of a material point P in relation to the moving reference frame, also known as the relative velocity, can be expressed as we can see here in this equation. In the laboratory reference frame, V here represents the average velocity, also referred to as the absolute velocity. The term VMRFT indicates the translation velocity of the moving reference frame, which is the velocity of its origin relative to the laboratory frame. The angular velocity of the moving reference frame is in relation to the laboratory frame is denoted by omega MRF, while RPMRF signifies the position vector of the material point in the context of the moving reference frame. The final term on the right hand side of the momentum equation accounts for the fictitious force that arises from the non-inertial moving reference frame. This fictitious force includes both the Coriolis force and the centrifugal force. When the reference frame is stationary, this fictitious force disappears and we have this equation. Therefore, as can be inferred from these two equations, the convective terms contain additional contributions due to the mesh velocity and moving reference frame. Thus, considering the discretized form of the convective terms, these contributions translate into an additional flux referred to as the grid flux. Overset meshes. Overset meshes discretize a computational domain with several different meshes that arbitrarily overlap. They are most useful in problems dealing with large motions and optimization studies where geometry can be enclosed in an overset region and set to different positions. The overset mesh, which contains the rigid body, is superimposed over a background mesh, which is usually stationary, as shown here in this figure, where the rotational and translational movements of a body are modeled. A critical advantage of the overset mesh technique is that it allows the simulation of complex motions. As shown in this figure, depending on their position within the computational domain, cells can be used as active, passive, or acceptor cells. Active cells are used for the simulation and the governing fluid flow equations are solved within them. Passive cells, also referred to as inactive cells, have no equations solved within them. Acceptor cells are located between active and inactive cells and facilitate the interpolation of information between the overset and background meshes. Consequently, the overset mesh technique connects different regions by exchanging data between acceptor cells from one region and donor cells designated active cells in another region. A standard overset simulation features a background region that encompasses the entire solution domain and one overset region that surrounds an object like a boat hull or an airfoil. The outer boundary of the overset region is designated as an overset boundary. To link these two regions, STAR-CCM Plus employs a hole cutting technique where cells that drive their solution exclusively from the overset regions are marked as inactive in the background region. Both the overset and background regions contain several layers of overlapping cells that are involved in the data exchange process. The solution is calculated for all active cells across all regions concurrently, making the meshes implicitly coupled. Within the discretized equation system, when a reference is made to the variable value in an acceptor cell of one region, a combination of variable values at donor cells from the other region is utilized to provide that value. This value is directly reflected in the coefficient matrix of the algebraic equation system. The close integration of the overset and background regions enables a solution with a minimal level of iteration errors, and therefore the convergence rate of the iterative solution method is comparable to that of a single mesh with the same resolution. A crucial aspect of effectively employing overset meshes is ensuring that the sizes of the cells are comparable and sufficiently large in the overlapping area between the background and overset regions. This overlapping area must consist of at least 4 to 5 cell layers in both the background and overset meshes. A significant consideration when utilizing and overset grid is determining the appropriate time step size. The time step size for an overset simulation is contingent on the mesh size. The time step should be configured such that the overset mesh does not travel more than the smallest cell size over the overlap area in the background region when the first order Euler scheme for time integration is employed. Half of the smallest cell size over the overlap area in the background region when the second order implicit time integration scheme is utilized. Another example is shown here in this figure. The cell types in the background region can be seen here. The cell types in the overset region and the final mesh combined from both regions. Overset meshes are most applicable in the following cases: parametric studies, including orienting identical bodies at different relative positions or immersing different bodies in the same environment. Fewer meshes are generated for these cases when using overset meshes. Complicated body motions, such as those involving closed bodies, have intersecting path or large motions. Methodology. Donor cells need to be identified for every acceptor cell. The selection of donor cells is influenced by the selected interpolation method and the count of active cells in the donor area surrounding the centroid of the acceptor cell. The interpolation options are: first, distance weighted interpolation involves using interpolation factors that are inversely related to the distance from the acceptor cell to the center of the donor cell, which means that the nearest cell provides the greatest contribution. In this process, 3 donor cells are used in 2 dimensions, 2D, or 4 in 3 dimensions, 3D. The entire overset assembly procedure is carried out at each time step. Second, linear interpolation with shape functions that cover a triangle in 2D or a tetrahedron in 3D is determined by the centroids of the donor cells. This option offers greater precision but also comes at a higher cost. In simulations that utilize moving meshes, it is crucial to prevent the interpolation elements from overlapping. The selection of donor cells is not definitive, since multiple donor cell centroids that encompass the acceptor cell centroid can create more than one triangle or tetrahedron. This ensures that the interpolation remains smooth as the acceptor cell centroid transitions from one interpolation element to another. In simulations with moving meshes, if the movement of the overset region relative to the cell size during single time step is minimal, the donor triangle in 2D or the donor tetrahedron in 3D can still be applicable. In such cases, only the interpolation factors need to be recalculated, avoiding the need to carry out the entire overset assembly process. For these scenarios, linear interpolation serves as an effective improvement in terms of runtime. Third, least squares interpolation. The least squares approach employs a cost function to estimate the distribution of the solution field close to a specific target. In this diagram, the solution field has defined values Fi at the centroid faces I of the source mesh. In order to assess the map value at the target point A, STAR-CCM Plus utilizes a first-order Taylor series to approximate the solution field F centered around A, as you can see here in this equation. Using the least square approach, STAR-CCM Plus calculates Fxa by reducing the total of squared residuals, as you can see here in this equation. Here, the residuals are calculated as the discrepancies between the values estimated by this equation at the source positions I and their corresponding known values Fi, as you can see here in this equation. Only the adjacent faces of the source that are nearest to the target face have a role in the interpolation. In this equation, the group of centroids from the faces that contribute is represented by Fc. In this illustration, face 0 is positioned nearest to face A. Only the neighbors of face 0, which are defined as any face that shares at least one vertex with face 0, are involved in the interpolation. The drawback is that some of the blue faces that project onto the target face, such as 1, 10, 11, and 7, do not play a role in this process. The interpolation function is integrated directly into the coefficient matrix of the algebraic equation system. This method guarantees implicit coupling of the overset meshes. In this image, two acceptor cells are depicted with dashed lines, one from the background mesh and the other from the overset mesh. Whenever the variable value at the centroid of the acceptor cell, indicated by the C symbols in this figure, is cited, the weighted variable values from the donor cells are used as substitutes. In this equation, alpha I are the interpolation weighting factors, phi I are the values of the dependent variable phi at donor cells ni, and subscript I runs over all donor nodes of an interpolation element denoted by the green triangles in this figure. This way, the algebraic equations for the cell C in this figure involves three neighbor cells from the same mesh Ni to N3 and three cells from the overlapping mesh N4 to N6. Morphing, dynamic deforming meshes. The morpher motion feature enables you to consider the impact of shifting boundaries in your analysis during a transient simulation. The morpher can be utilized, for instance, to replicate the back and forth motion of a piston within a cylinder where the outer limits remain unchanged, but the mesh vertices need to adjust to fit the movement. The morpher is also applicable in situations where the boundary shape is altering, as shown here in this figure. The morphing motion feature in STAR-CCM Plus adjusts the positions of mesh vertices based on the movement of a designated set of control points, which can be thought of as a cluster of points projected onto the mesh area. The control points and their corresponding displacements create the essential structure that the morpher needs to produce an interpolation field. To achieve this, a series of control points, each linked with a known displacement vector, is utilized to establish an interpolation field across the entire computational domain. This interpolation field is subsequently employed to represent the motion of the morpher, facilitating the movement of the mesh vertices to their updated positions. One approach involves utilizing the radial basis function RBF as the method for interpolation. The RBF technique formulates a set of equations to create the interpolation field. This set of equations is generated by utilizing the control points gathered from the boundaries and their corresponding displacements, as we can see here in this equation. Here, di prime is the known displacement of each control vertex I. If bj as a function of rij indicates a radial basis function, which is defined as we can see here, where rij is the distance magnitude between two vertices. Lambda j here is the expansion coefficient, xi is the position of vertex I, and n is the number of control vertices. The constant alpha vector here is employed to impose the following additional constraint to bound the expansion for large x values. The system that is presented here in this equation is not singular if xi does not equal to xj for all I does not equal to j. By solving these two equations, one can obtain the Cartesian components of all lambda j along with the components of the constant vector alpha. This gives the intended interpolation field as we can see here. Here, f bj as a function of r is applied to all mesh vertices and is defined as we can see here. Thus, this equation can now be employed to translate the mesh vertices by using the calculated displacement d prime. Adaptive mesh refinement. Adaptive mesh refinement, AMR, is a dynamic technique that adjusts the mesh density by refining or coarsening cells in accordance with adaptive mesh criteria as they evaluate the flow solution. Solution quantities are seamlessly interpolated to the modified mesh. AMR enhances the volume mesh's capability to capture the desired fluid flow characteristics, but it does not negate the necessity for meticulous mesh construction. Implementing adaptive mesh refinement requires the initial mesh to contain a sufficient number of cells to depict the overall flow behaviors. Furthermore, the surface mesh of the initial setup must adequately represent the CAD geometry, given that AMR does not provide any surface reconstruction capabilities. As illustrated in this figure, for a maneuvering vessel, utilizing AMR can significantly decrease the number of cells in the computational domain, resulting in a notable reduction in computational costs. Stationary mesh in moving reference frame. In steady simulations or transient simulations that do not require a time-accurate simulation, moving reference frames provides a way of modeling rigid rotations and translations as a steady-state problem while leaving the mesh stationary. Moving reference frames can rigidly rotate or rotate and translate relative to the laboratory frame. For flows around rotating machinery, STAR-CCM Plus also provides simplified approaches that approximate the effect of a rotating structure on the surrounding flow field without the need for mesh motion, moving reference frames, or detailed modeling of the structure geometry. STAR-CCM Plus provides many possibilities for simulating rotating flows. These possibilities include using moving reference frames or rigid body motion involving mesh motion. Both approaches require the resolution of the detailed blade geometry, leading to a large number of cells, which increases analysis runtime and hardware requirements. A further option to model rotating flows is to use simplified approaches that model the effect of rotating machinery on the surrounding flow field by adding volumetric body forces to the momentum equations or imposing a pressure jump across a plane surface. These approaches are described in the following sections. In steady-state simulations or transient simulations that do not require precise time information, moving reference frames offer a method to represent rigid rotations or translations as a steady-state problem while keeping the mesh fixed. Moving reference frames can rotate rigidly or perform both rotation and translation in relation to the laboratory frame. For simulations involving flow around rotating equipment, STAR-CCM Plus also offers simplified methods that estimate the influence of a rotating structure on the nearby flow field without needing mesh movement, moving reference frames, or intricate structure geometry modeling. STAR-CCM Plus presents various options for simulating rotating flows, and these options consist of utilizing moving reference frames or rigid body motion that involves mesh movement. Both methods necessitate the detailed resolution of blade geometry, resulting in a large number of cells, which increases analysis runtime and hardware demands. An additional method for modeling rotating flows is to apply simplified techniques that represents the impact of rotating machinery on the surrounding flow field by introducing volumetric body forces into the momentum equations or enforcing a pressure differential across a defined plane surface. These methods are detailed in the subsequent sections. Virtual disk model. The virtual disk model defines devices like propellers, turbines, rotors, and fans as an actuator disk. This actuator disk approach is useful when the focus is on how the behavior of the rotor or propeller affects the flow rather than understanding the specific interaction between the flow and the blades of the rotating device. The actuator disk effect on the flow field is incorporated into the momentum equations as a source term. The chosen virtual disk method provides the source term distribution in the radial direction. Conversely, a Gaussian shape function describes the distribution in the thickness direction. Here, in this figure, we can see the propeller versus a virtual disk behind a submarine. Body force propeller method. The body force propeller technique is employed to simulate the impact of a propeller, including thrust and torque, thus generating propulsion without directly dealing with the geometry of the propeller. This approach uses a consistent volume force FB distribution across a cylindrical virtual disk. The volume force changes along the radial direction. The radial distribution of the force components adheres to the Goldstein optimum and is expressed by these equations. Here, Fbx is the body force component in axial direction. Fb theta is the body force component in tangential direction. R is the radial component. Rh is the hop radius. And Rp is the propeller tip radius. The constants Ax and A theta are computed as we can see here in these equations. Here T is the thrust, Q is the torque, and delta is the virtual disk thickness. To calculate the components of the body force, several inputs from the user are necessary. A propeller performance curve must be provided detailing the dimensionless thrust coefficient KT, the torque coefficient KQ, and the propeller efficiency eta 0 as a function of the advanced coefficients, advanced ratio J. Additional inputs required include the location of the propeller within the computational domain, the orientation of the propeller's rotational axis, and the direction of its rotation. The simulation is conducted at a specific operating point which can be defined by any of these parameters, either rotation rate, thrust, or torque. Blade element method. It is primarily designed to model the effects of a helicopter rotor on the flow field without prescribing the exact geometry of rotor blades. This approach consists of two parts. The first step is to identify the location of cells within the computational domain that belong to the virtual disk and to which the source term is applied. The second step involves calculating the momentum source term vector for each cell, which was identified and marked in the first step. Step 1. Cell marking and the allocation to the blade elements buckets based on the interpolation grid. The information for this step is user specified and provided through the virtual disk nodes. Disk geometry describes the geometrical dimensions and the orientation of the disk. Virtual disk resolution specifies the size of the two-dimensional interpolation grid in polar coordinates representing the actual blade elements. The blade properties such as chord, twist, and aerodynamic characteristics prevail throughout the element. Source term distribution, time average. For the time average approach, the source term is calculated per blade element on the interpolation grid and then transferred to the finite volume mesh. Each element is associated with a number of cells on the finite volume mesh. For the coupling between the local flow conditions and the modeled rotor, the information is taken from the finite volume cell, which is the closest to the center of a blade element on the interpolation grid. Thus, the specified size of the interpolation grid is the actual computational effort of the influence of the rotor on the flow field. This sketch explains the flow field coupling between the finite volume mesh red and the virtual disk interpolation grid black. The marking procedure is itself a two-step procedure. First, all the cells that fall within the circular disk area are marked to receive the source term. Second, each of the marked cells is assigned a bucket element number corresponding to its location with respect to the interpolation grid. So each of the cells that was marked during the first step belongs to one of the elements buckets of the interpolation grid. This approach requires that each element bucket has at least one cell in its domain. If the finite volume mesh is very coarse and the interpolation grid is too fine, then you are asked to reduce the resolution. The following two figures show the interpolation grid for two different resolutions. For the fine interpolation grid, in the second figure, no finite volume cell come under the domain of some for some of the elements buckets at the innermost radius, as we can see here in this figure. Source term distribution, time accurate. The time accurate approach tracks the blade's motion and adds source terms only to the volume cells that correspond to their location. For the rotor with 4 blades, the cells are marked as shown here in this figure according to the blade shape and location specified within the disk geometry node. To ensure successful coupling with the interpolation grid, the finite volume mesh must be sufficiently fine that at least 5 cells are marked across the blade width. A similar mesh resolution should be applied for the entire swept area of the rotor. In the example above, 10 cells are marked. Step 2. Calculation of momentum source term strength. The second part of the blade element method calculates the strength of the momentum source term for the elements on the interpolation grid. The source terms are calculated using the drag and lift coefficients of the airfoil elements along the blades. Knowing the angle of attack alpha and the blade relative velocity, shown typically by V rel, experienced by the airfoil, these coefficients are calculated as a function of either the Mach number or the Reynolds number. 1D momentum method. A wind turbine extracts mechanical energy from the kinetic energy of the wind. It acts as an actuator disc, slowing down the wind speed from u0 to u at the rotor plane and further slowing it down to u1 in the wake. Moving upstream to downstream, the velocity decreases and the streamlines diverge to comply with continuity. The 1D momentum method adds a source term to the momentum equations to model the effects of a wind turbine. The source term accounts for both the axial and the tangential effects as given by the ideal horizontal axis wind turbine with wake rotation. When wake rotation is included in the analysis, the induced velocity at the rotor consists of an axial component A and a tangential component A prime acting in the rotor plane. The formulation is based on the use of an annular stream tube with a radius r and a thickness dr. Note that this is not the disk thickness. This definition results in a cross-sectional area dA of 2 pi times r times dr. The following figure shows the schematics and the notation that is used in the formulation. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.